Hi, this is Ranella Puyat, BSIT, and today I will be presenting my course project in Data Communications and Networking for Network Security and Monitoring 1. The network administrators must know how to mitigate the attacks such as the telnet exploitation attack, the MAC address table flooding, the VLAN attacks, and the DHCP-related attacks. Securing the administrative access well using AAA and securing port access using 802.1x. Simple Network Management Protocol or SNMP. It is a networking protocol used for the management and monitoring of network-connected devices in Internet Protocol networks. It provides a common mechanism for network devices to relay management information within single and multi-vendor LAN or WAN environments. Commonly used to collect information. The common LAN attacks. Common LAN attacks against the Layer 2 LAN infrastructure includes the CTP reconnaissance attack, the telnet attacks, the MAC address table flooding attack, VLAN attacks, and DHCP attack. The first two is where the attackers are focused on gaining the administrative access to the network device, while the last other three is when the attackers are focused on disrupting the network operation. Cisco Discovery Protocol or CDP. It is a proprietary Layer 2 link discovery protocol. It is enabled on all Cisco devices by default. CDP can automatically discover other CDP-enabled devices and help auto-configure their connection. Network administrator also use CDP to help configure and troubleshoot network devices. Wireshark. It is a free and open source packet analyzer. It is used for network troubleshooting, analysis, software, and communications protocol development and education. Wireshark captures display and contents of a CDP packet. The attacker is able to identify the Cisco iOS software version used by the device. This allows the attacker to determine whether there were any security vulnerabilities specific to that particular version of iOS. The CDP reconnaissance attack is where the attacker is able to identify the Cisco iOS software version used by the device. This allows the attacker to determine whether there were any security vulnerabilities specific to that particular version of iOS. So here in the illustration, we can see that the Wireshark captured the software version from the CDP frame. So it says that the software version Cisco iOS software is detected and identified by the Wireshark. To mitigate the exploitation of CDP, the administrator should limit the use of CDP on devices or ports. So note that the link layer discovery protocol or LLDP is also vulnerable to reconnaissance attack. So configure the no LLDP run to disable the LLDP globally, and to disable the LLDP on the interface, configure the no LLDP transmit and the ability to remotely manage a switch LAN infrastructure is an operational requirement. Therefore, it must be supported. However, the telnet protocol is inherently insecure and can be leveraged by an attacker to gain remote access to a Cisco network device. There are tools available that allow an attacker to launch attacks against the VTY LANs on the switch. Telnet attacks. There are two types of telnet attacks. The first one is the brute force password attack. The attacker may use a list of common passwords, dictionary words, and variations of words to discover the administrative password. If the password is not discovered by the first phase, a second phase begins. And then the other one is the telnet DOS attacks. So this is when the attacker continuously requests telnet connections in an attempt to render the telnet service unavailable and prevent an administrator from remotely accessing a switch. This can be combined with other direct attacks on the network as a part of a coordinated attempt to prevent the network administrator from accessing core devices during the breach. Telnet attacks. There are several ways to mitigate against telnet attacks. The first is to use the SSH rather than telnet for remote management connections. Use strong passwords that are changed frequently. A strong password should have a mix of upper and lowercase letters and should include numerals and symbols, special characters. Limit access to VTY LANs using an access control list or ACL, permitting only administrator devices and denying all other devices. Authenticate and authorize administrative access to the device using AAA with either TACACS or plus or Radius protocols. MAC address table flooding attack. One of the most basic common LAN switch attack is the MAC address flooding attack. This attack is also known as MAC address table overflow attack or a CAM table overflow attack. So an attacker can exploit this default switch behavior to create MAC address flooding attack. MAC address tables are limited in size. MAC flooding attacks exploit this limitation with fake source. MAC address until the switch MAC address table is full and the switch is overwhelmed. The MAC address table becomes full of fake MAC addresses. Okay. And then enters into what is known a fail open mode. In this mode, the switch broadcasts all frames of all machines on the network. As a result, the attacker can capture all the frames, even frames that are not addressed to its MAC address table. And then to mitigate the MAC address table flooding attack the simplest and the most effective method is to prevent the MAC table flooding attacks is to enable the port security. Cisco switches are packed with built-in security features against MAC flooding attacks called as port security. The port security is a feature of Cisco switches which give protection against MAC flooding attacks. Okay, to disable the DTP auto-trunking negotiations on non-trunking ports and explicitly force the access ports by using the switch port mode access interface configuration command. Then manually enable the trunk link on a trunking port using the switch port mode trunk interface and configuration command. Disable the DTP auto-trunking negotiations on trunking and non-trunking ports using the switch port no negotiate interface configuration command. And then the other one is to set the native VLAN to be something other than VLAN 1. So it is on unused VLAN using the switch port trunk native VLAN or the VLAN number interface configuration mode command. Disable the unused ports and assign them to an unused VLAN. The VLAN attacks. This illustrates one type of VLAN threat, which is the port spoofing attack. The attacker attempts to gain VLAN access by configuring the host to spoof switch and use the 802.1q trunking protocol and the switch proprietary dynamic trunking protocol or DTP. So the DTP feature to trunk with the connection switch. If successful and switch establishes a trunk link with the host, and the attacker can then access the VLANs on the switch and hop. So this is an example of the send and receive traffic of all to the VLANs. Mitigate the VLAN attacks. Okay. There are several ways to mitigate VLAN attacks. First is to explicitly configure access link or explicitly disable auto-trunking, manually enable trunk links, and disable unused ports, make them access ports, and assign them to a black hole VLAN. And then change the VLAN native VLAN and change the default native VLAN. Okay. Implement port security. And then for the DHCP attacks, the DHCP is the protocol that automatically assigns a host a valid IP address out of DHCP pool. So this is an example illustration of a rogue DHCP attacker, where there are two types of DHCP attack that can be performed against the switch network attack. The first is the DHCP spoofing attack and the DHCP starvation attack. The DHCP spoofing attack, wherein the attacker configures the fake DHCP server on the network to issue IP addresses to clients. This type of attack forces the client to use both a false domain name system or DNS server and computer which is under the control of the attacker as their default gateway. While the DHCP starvation attack, an attacker floods the DHCP server with bogus DHCP requests and eventually leases all the available IP address in the DHCP server pool. After these IP addresses are issued, the server cannot issue any more addresses, and this situation produces a denial of service or DOS attack. Okay, to mitigate the DHCP attacks, security best practices recommend using DHCP snooping to mitigate DHCP spoofing attacks. This is when the DHCP snooping is enabled on an interface or VLAN and the switch receives a DHCP packet on an untrusted port. The switch compares the source packet information with the held in DHCP snooping binding database. The switch will deny packets containing any of the following information. The first is the unauthorized DHCP server messages coming from an untrusted port. And the other one is unauthorized DHCP client messages not adhering to the DHCP snooping binding database or rate limits. And the other one, in the large network, the DHCP snooping binding database may take time to build after it is enabled. For example, it could take 2 days for a DHCP snooping to complete the database if the DHCP list time is 4 days. DHCP ports. DHCP snooping recognizes two types of ports. The trusted DHCP ports, wherein only ports connecting to upstream DHCP servers should be trusted. These ports should lead to legitimate DHCP servers replying with DHCP offers and DHCP ACK messages. Trusted ports must be explicitly identified in the configuration. And the other one is the untrusted ports, wherein these ports connect to hosts that should be providing DHCP server messages. By default, all switch ports are untrusted. The figure provides a visual example of how DHCP snooping ports should be assigned on a network. Notice how the trusted ports always lead to legitimate DHCP server, while all other ports, access ports, connecting to endpoints are untrusted by default. Secure administrative access using AAA. AAA means Authentication, Authorization, and Accounting Framework. It is used to help secure device access. AAA authentication can be used to authenticate users for administrative access, or it can be used to authenticate users for remote network access. Secure device access using 802.1x. Network user authentication can be provided by AAA server-based authentication. The 802.1x protocol or standard can be used to authenticate network devices on the corporate network. There is another protocol used to secure computers connecting to a LAN. AAA authentication. Cisco provides two common methods of implementing AAA services. Local AAA authentication, wherein local AAA uses a local database for authentication. This method is sometimes known as self-contained authentication. This method stores username and passwords locally in Cisco router, and then the users authenticate against the local database. Local AAA is ideal for small networks only. And then the server-based AAA authentication, wherein the server-based AAA authentication is much more scalable solution. With the server-based method, the router accesses a central AAA server, and the AAA server contains the username and passwords for all users and servers as a central authentication system for all infrastructure devices. 802.1x rows. So, these are the rows for the 802.1x. So, the supplicant, the authenticator, and the authentication, wherein the supplicant requires an access and response to requests from switch. And then the authenticator will control the physical access to the network device, network based on client authentication status, while the authentication performs the client authentication. Okay. Simple Network Management Protocol. Simple Network Management Protocol was developed to allow administrators to manage nodes such as servers, workstations, routers, switches, and security appliances on an IP network. It enables network administrators to monitor and manage network performance, find and solve network problems, and map in an application layer protocol that provides a message format for communication between managers and agents, and plan for network growth. SNMP defines how management information is exchanged between network management applications and management agents. The SNMP managers polls the agents and queries the MIB for SNMP agents on UDP port 161. And SNMP agents send any SNMP traps to the SNMP manager. The three elements of SNMP: the SNMP manager, SNMP agent, and MIB. The SNMP manager is a part of Network Management System or NMS. The SNMP manager runs SNMP management software. The SNMP manager can collect information from the SNMP agent using the GET action and can change configuration on an agent using the SET action. In addition, SNMP agents can forward the information directly to a manager using the traps. The two primary SNMP manager requests are the GET request and the SET request. wherein the GET request is used by the NMS to query the device for data, and the SET request is used by the NMS to change configuration variables in the agent device. The SNMP agent and MIB reside on SNMP client devices, network devices that must be managed, such as switches, routers, servers, firewalls, and workstations are equipped with an SNMP agent software module. MIBs store data about the device and operational statistics and are meant to be available to authenticated remote users. The SNMP agent is responsible for providing SNMP operations. Get request retrieves a value from a specific variable. Get next request it retrieves a value from a variable within the table. The SNMP manager does not need to know the exact variable name. A sequential search is performed to find the needed variable from within the table. Get bulk request retrieves large blocks of data, such as multiple rows in a table, that would otherwise require the transmission of many small blocks of data. It will only works with SNMP version 2 or later. Get response is replies to a get request, get next request, and set request sent by an NMS. And then the get request stores a value to a specific SNMP operations. The SNMP agent responds to SNMP manager requests as follows. Get an MIB variable. The SNMP agent performs these functions in response to a get request PDU from the network manager. The agent retrieves the value of the requested MIB variable and responds to the network manager with that value. So, set an MIB variable. The SNMP agent performs this function in response to a set request PDU from the network manager. The SNMP agent changes the value of the MIB variable to the value specified by the network manager. An SNMP agent reply to a set request includes the new setting in the device. SNMP agent traps. The NMS periodically polls the SNMP agents residing on managed devices by querying the device for data using the GET request. Periodic SNMP polling does have an advantage. First, there is a delay between the time that the event occurs and the time that it is noticed via polling with the NMS. Second, there is a trade-off between the polling frequency and bandwidth usage. To mitigate the SNMP agent traps, this is the advantage. It is possible for the SNMP agents to generate send traps to inform the NMS immediately in certain events. Traps are unsolicited messages alerting the SNMP manager to a condition or event on the network. Examples of trap conditions include, but are not limited to, improper user authentication, restarts, link status up or down, MAC address tracking, closing of TCP connection, loss of connection to a neighbor, or other significant events. Trap-directed notification reduce network and agent resources by eliminating the need for some of SNMP polling requests. SNMP versions. SNMP version 1, the Simple Network Management Protocol, a full Internet standard defined in RFC 1157. SNMP version 2, defined in RFC 1901 to 1908. utilizes community string-based administrative framework. SNMP version 1 and SNMP version 2 offer minimal security features. The SNMP version 3 is interoperable, standard-based protocol originally defined in RFC 2273 and 2275. Provides secure access to devices by authenticating and encrypting packets over the network. The SNMP version 3 provides for both security models and security levels. Community strings. For SNMP to operate, the NMS must have access to the MIB. To ensure the access requests are valid, some form of authentication must be in place. The SNMP version 1 and the SNMP version 2 use community strings that control access to the MIB. Community strings are plain text passwords. SNMP community strings authenticate access to MIB objects. There are two types of community strings: the read-only and the read and write. The read-only provides access to MIB variables but does not allow these variables to be changed. Only read. Because security is minimal in version 2, many organizations use SNMP version 2C in read-only mode, while the read and write or RW provides read and write access to all objects in the MIB. Okay, management information-based object. The MIB organizes variables hierarchically. MIB variables enable the management software to monitor the control the network device. Formally, the MIB defines with each variable as an object ID or OID. SNMP graphing tool. CPU is one of the key resources. It should be measured continuously. CPU statistics should be compiled on the NMS graph. SNMP get utility. The data is retrieved via SNMP get utility issued on the NMS. Using the SNMP get utility, one can manually retrieve real-time data or have the NMS run a report which would give you a period of time that could use the data to get the average. SNMP Object Navigator. The Cisco SNMP Navigator on the http cisco.com website allows the network administrator to research details about particular OID. Figure 6.24, which is shown in the left side, Network Security and Monitoring Tool. Span Overview. The port mirroring. A packet analyzer, also known as a sniffer, packet sniffer, or traffic sniffer, is a valuable tool to help monitor and troubleshoot a network. A packet analyzer is typically software that captures packets entering and exiting a network interface card or NIC. For example, Wireshark is a packet analyzer that is commonly used to capture and analyze packets on a local computer. The port mirroring feature allows a switch to copy and send Ethernet frames from specific ports to the destination port connected to a packet analyzer. The original frame is still forwarded in the usual manner. Span Overview. Analyzing suspicious traffic. The switch port analyzer or span feature on Cisco switches is a type of port mirroring that sends copies of the frame entering a port out of another port on the same switch. Span allows administrators or devices to collect and analyze traffic. So the packet analyzers using software such as Wireshark to capture and analyze traffic for troubleshooting purposes. While the intrusion prevention system or IPSS are focused on the security aspect of traffic and are implemented to detect network attacks as they happen, issuing alerts or even blocking the malicious packets as the attack takes place. IPS are typically deployed as a service on a ISRG2 router or using a dedicated device. Span overview. So the local span is when a traffic or on a switch is mirrored to another port on that switch. Various terms are used to identify incoming and outgoing ports. Okay. This is an example of illustration wherein the local span where the source port ingress and then the source port egress and destination port monitor port. There are three important things to consider when configuring a span. The destination port cannot be a source port, and the source port cannot be a destination port. Okay? The number of destination ports is platform dependent. Some platform allows for more than one destination port. And then the destination port is no longer a normal switch port. Only monitored traffic passes through that port. The span feature is set to be local but monitored ports are all located on the same switch as the destination port. This features is in contrast to remote span or RS span. The remote span. The RS span allows source and destination ports to be in different switches. RS span is useful when packet analyzer or IPS is on different switch than the traffic being monitored. RS span uses two sessions. One session is used as the source and the other session is used to copy and receive the traffic from a VLAN. The traffic for each RS span session is carried over trunk links in user-specified RS span VLAN that is dedicated for RS span session in all participating switches. Span configuration. The span feature on Cisco switches sends a copy of each frame entering the source port out of the destination and toward the packet analyzers of IPS. A session number is used to identify a local span session. So this is an example of configuration or configuring the span feature on Cisco. Okay, this is an example configuration for verifying the local span. So we have here the switch and then the PCA, and let's say we have here the PC2 which has the packet analyzer in it. So have to configure the S1 with 120 and then monitor session 1 source interface dot 01. Okay, and then monitor session 1 for the destination. Okay. Interface fast Ethernet 02. Okay. And then show. Okay. Okay, and then show monitor. Right. Monitor. Okay. Oh, and then show monitor. Okay. Okay. The configuration show that the session 1 type is a local session wherein we have I already configure the F01 as a source port and then the F02 as a destination port, wherein the encapsulation is native and ingress is disabled. Span as troubleshooting tool. Troubleshooting with Span overview. Span allows administrators to troubleshoot network issues. Older systems with faulty NICs can also cause issues. If Span is enabled on switch to send traffic to a packet analyzer, a network technician can detect and isolate the end device causing the excess traffic. So these are the terminologies that we have used in this chapter. The span terminology, which is the egress, the egress, the source span port, and the destination port, span session, and source VLAN. So in RS span terminology, the RS span source session, the RS span destination and session, RS span VLAN, wherein the egress traffic means that the traffic enters the switch, and then the egress traffic means that it is the traffic that leaves the switch. The source span port is the port that is monitored with the use of span feature. The destination span port, this is the port monitor source port, usually where the packet analyzer, IDS or IPS is connected. This port is also called the monitoring port. The span session, this is an association of destination port with one or more source ports. And the source VLAN is the VLAN monitored for traffic analysis. RS span terminology, wherein the RS span source session, this is the source port VLAN to copy traffic form. And then the RS span destination session is the destination VLAN port to send the traffic to. And then the RS span VLAN is the unique VLAN is required to transport the traffic from one switch to another. The VLAN configured with the remote span VLAN configuration command. And this VLAN must be defined on all switches in the path and must also be allowed to trunk ports between the source and the destination. Quality of service, part 1. Network transmission quality. Prioritizing traffic. Quality of service or QoS is an ever-increasing requirement of network today. New applications available to users such as voice and live video transmission create higher expectation of quality delivery. Congestion occurs when multiple communication lines aggregate into single device such as a router, and then much of the data is placed on fewer outbound interfaces onto a slower interface. Congestion also occurs when large data packets prevent smaller packets from being transmitted in a timely manner. When the volume of traffic is greater than what can be transported across the network, devices queue and hold the packets in memory until the resources become available to transmit them. Queuing packets causes delay because new packets cannot be transmitted until the previous packet have been processed. If the number of packets to be queued continues to increase, the memory within the device fills up, the packets are dropped. Bandwidth, congestion, delay, and jitter. Network bandwidth is measured in number of bits that can be transmitted in a single second, or bits per second, or BPS. The network congestion causes delay, and the interface experiences congestion when it is presented with more traffic than it can handle. Network congestion points are strong candidates for QoS mechanisms. Bandwidth congestion, delay, and jitters. Continuation. Delay or latency refers to the time it takes for a packet to travel from the source to the destination. The two types of delays are the fixed delay and the variable delay. The fixed delay is a specific amount of time a specific process takes, such as how long it takes to place a bit on the transmission data, while the variable delay take an unspecified amount of time and is affected by factors such as how much traffic is being processed. The sources of delays are code delay, wherein the fixed amount of time it takes to compress data at the source before transmitting to the first internet working device, usually a switch. Packetization delay, wherein the fixed time it takes to encapsulate a packet with all the necessary header information. The queuing delay is the variable amount of time a frame or packet waits to be transmitted on the link. The serialization delay is the fixed amount of time it takes to transmit a frame onto the wire. The propagation delay is the variable amount of time it takes for a frame to travel between the source and the destination. And the jitter delay is the fixed amount of time it takes a buffer flow of packets and then send them out in evenly spaced intervals. The sources of delays are the jitter, the packet loss. The jitter is the variation in delay of received packets, and the sending slides packets are sent in continuous stream with the packets spaced evenly apart. While the packet loss is very common cause of voice quality problems on an IP network, it is a properly in a properly designed network, packet loss should be near zero. Traffic characteristics. Okay. The type of demands of voice, video, and data traffic placed on a network are very different. For voice, the voice traffic is predictable and smooth. Voice is very sensitive to delays and drop packets. Voice packets must receive a higher priority than other types of traffic. And then voice can tolerate a certain amount of latency jitter and loss without a noticeable effects. Latency should be no more than 150 milliseconds, and then jitter should be no more than 30 milliseconds. And the voice packet loss should be not more than 1%. Voice traffic requires at least 30 kbps bandwidth. The traffic characteristic and the other one is the video. Without the QoS and significant amount of extra bandwidth capacity, video quality typically degrades. The picture appears blurry, jagged, or in slow motion. The audio portion of the feed may become unsynchronized with the video. The video traffic tends to be unpredictable, inconsistent, and burst compared to voice traffic. Compared to voice, video is less resilient to loss and has a higher volume of data per packet. The number of size of video packets vary in 33 ms based on the content of the video. And then the video streams consists of content that is rapidly changing, such as an action sequence in a movie. Then the video packet will be larger and more required per 33 ms time slot to maintain an acceptable user experience. Traffic characteristic, and the other one is data. Most applications use their TCP or UDP. Unlike UDP, TCP performs error recovery. Data applications that have no tolerance for data loss, such as emails and web pages, use TCP to ensure that if packets are lost in transit, they will be resent. Data traffic can be smooth or bursty. Network control traffic is usually smooth and predictable. When there is a topology change, the network control traffic may burst for a few seconds, but the capacity of today's networks can easily handle the increase in network control. However, some TCP applications can be very greedy, consuming a large portion of network capacity. FTP will consume as much bandwidth as it can get when you download a large file, such as a movie game. Factors to consider for data delay. Quality of experience, or QoE. Although data traffic is relatively sensitive to drops and delays compared to voice and video, a network administrator still needs to consider the quality of the user experience. So these are the factors to consider for data delay: the interactive and non-interactive, wherein the interactive prioritize for the lowest delay of all data traffic and strive for 1 to 2 seconds response time. And then the not interactive delay can vary greatly as long as the necessary minimum bandwidth is supplied. This is not the mission critical for interactive. Application could benefit from lower delay. And then for not interactive, the not mission critical gets any leftover bandwidth after all voice, video, and other data application needs are met. Queuing algorithms. Queuing is a congestion management tool that can buffer, prioritize, and if required, reorder packets before being transmitted to the destination. The first in, first out, or FIFO. The weighted fair queuing, or WFQ. The class-based weighted fair queuing, or CBWFQ. The low latency queuing, or LLQ. The queuing algorithms. The FIFO, in its simplest form, FIFO, queuing, also known as first come first serve. Queuing involves buffering and forwarding of packets in the order of arrival. It is the fastest method of queuing. It is effective for large links that have a little delay and minimal congestion. If your link has very little congestion, FIFO queuing may be the only queuing that you need to use. The weighted fair queuing, or WFQ, is an automated scheduling method that provides fair bandwidth allocation for all network traffic. WFQ applies priority or weights to identify the traffic and classifies it into conversations or flows. Then it determines how much bandwidth each flow is allowed relative to other flows. WFQ is not supported with tunneling and encryption because these features modifies the packet content information required by WFQ or classification. The WFQ automatically adapts to changing network traffic condition. It does not offer the degree of precision control over bandwidth allocation the CBWFQ offers. So this is an example illustration of weighted fair queuing. Okay, that it has a scheduling method. And then the other one is the class-based weighted fair queuing, wherein it extends the standard WFQ functionality to provide support for user-defined traffic classes. For CBWFQ, you define traffic classes based on the match criteria, including the protocols, access control lists or ACLs, and input interfaces. Packets satisfying the match criteria for a class constitute the traffic for that class. To characterize a class, you also specify the queue limit for that class, which is the maximum number of packets allowed to accumulate in the queue for the class. Packets belonging to a class are subject to the bandwidth and queue limits that characterize the class. After the queue has reached its configured queue limit, adding more packets to the class causes tail drop or packet drop to take effect, depending on how the class policy is configured. Low latency queuing or LLQ. The LLQ features brings strict priority queuing or PQ to CBWFQ. Strict PQ allows delay sensitive data such as voice to be sent before the packets in other queues. LLQ provides strict priority queuing for CBWFQ, reducing jitters in the voice conversation. With LLQ, delay-sensitive data is sent first before the packets in other queues are treated. LLQ allows delay-sensitive data such as voice to be sent first before the packet in other queues, giving delay-sensitive data preferential treatment over other traffic. Although it is possible to enqueue various types of real-time traffic to the streak. So this is an example illustration of the low latency queuing wherein the data are set to priorities before sending. The quality service part 2. QoS mechanism. So the three models for implementing QoS are the best effort model, the integrated service, and then the differentiated services. For the best effort model, the basic design of the internet provides for best effort packet delivery and provides no guarantees. This approach is still predominant on the internet today and remains appropriate for most purposes. The best effort model treats all the network packets in the same way. So an emergency voice message is treated the same way a digital photo attached to an email is treated. And these are the benefits and drawbacks of the best effort. So the model is the most scalable. The scalability is only limited by bandwidth limits, in which case all traffic is equally affected. So no special QoS mechanisms are required, and the easiest and the quickest model to deploy. While the drawbacks for the best effort are there are no guarantees of deliveries, and then the packets will arrive whenever they can and in any order possible if they arrive at all, and then no packets have preferential treatment, and then the critical data is treated the same as casual email as treated. So for the other QoS mechanism is the IntServe. Okay. It provides a way to deliver the end-to-end QoS that real-time application require by explicitly managing network resources to provide QoS to a specific user packet stream, sometimes called as microflows. It uses resources reservations and admission control mechanism as building blocks to establish and maintain QoS. The practice is similar to a concept known as hard QoS. Hard QoS guarantees traffic characteristics such as bandwidth, delay, and packet loss rates from end to end. Hard QoS ensures both predictable and guaranteed service levels for mission-critical applications. Okay. And then the in-service uses a connection-oriented approach inherited from telephony network design. Each individual communication must explicitly specify its traffic descriptor and requested resources to the network. The end router performs admission control to ensure that the available resources are sufficient in the network. The int-serve standard assumes that routers along the benefits and drawbacks in int-serve are as follows. The benefits are explicit end-to-end resource, admission control, per request policy admission control, and then signaling of dynamic port numbers. And for the drawbacks, resource intensive due to a stateful architecture requirement for continuous signaling. The flow-based approach is not scalable to large implementations such as the internet. For differentiated services, or DiffServ QoS model specifies a simple and scalable mechanisms for classifying and managing network traffic and providing QoS guarantees on modern IP networks. For example, DiffServ can provide low latency guaranteed service to critical network traffic such as voice or video while providing simple best effort traffic guarantees to non-critical services such as web traffic or file transfer. And then the DiffServ design overcomes the limitation of both the best effort and the int-serve models. The DiffServ models is described in RFC 2474, 2597, 2598, 3246, and 4594. This DiffServ can provide an almost guaranteed QoS while still being cost-effective and scalable. The DiffServ model is similar in concept to send a package using a delivery service. Your request and pay for as a level of service when you send the package. So throughout the package network, the level of service you paid for is recognized and your package is given either preferential or normal service depending on what you have requested. Benefits and drawbacks. And for the benefits, it is highly scalable and provides many different levels of qualities. For the drawbacks, no absolute guarantee is service quality. And then it requires a set of complex mechanisms to work in concert throughout the network. The QoS implementation technique, avoiding packet loss. Packet loss is usually a result of congestion on an interface. Most applications that use TCP experience is slowed down because TCP automatically adjusts to network congestion. Drop TCP segments cause TCP sessions to reduce their window sizes. Some applications do not use TCP and cannot handle drops. QoS tools. Classification and marking tools, congestion and avoidance tools, congestion management tools. Tools for implementing QoS, the classification and marking tools. These sessions or flows are analyzed to determine what traffic class they belong to. Once they are determined, the packet is marked. Congestion avoidance tools is the traffic classes are allotted portions of the network sources as defined by the QoS policy. And then the QoS policy also identifies how some traffic may be selectively dropped, delayed, or remarked to avoid the congestion. And then the primary congestion avoidance tools, the WRED, and is used to regulate the TCP data traffic in the bandwidth efficient manner before tail drops caused by queue overflow occurs. And then the last one is the congestion management tool. When the traffic exceeds available network resources, traffic is queued to await the availability of resources. And then the common Cisco iOS-based congestion management tools include the CBWFQ and the LLQ algorithms. The QoS sequence. So we can see here in the given illustration that the ingress packets gray squares, which are the gray squares, are classified. And then after classifying, the respective IP header is marked. Those are the colored squares. And then to avoid the congestion, packets are allotted resources based on the defined policies. Okay. And then, after the policies, the packets are then queued and forwarded out the egress interface based on their defined QoS shaping and policing policy. And then the last one is the scheduling and the shaping, wherein the classification and marking can be done on egress, ingress, or egress. Whereas the QoS action, such as queuing and shaping, are usually done on egress. Classification and marking. The classification and marking allow us to identify or mark types of packets. The classification determines the class of traffic to which packets or frame belong. Only after traffic is marked can policies be applied to it. And then the marking means that we are adding a value to the packet header. Devices receiving the packet look at this field to see if it matches the defined policy. Marking should be done as close as the source device as possible. This establishes the trust boundaries. The layer 2 marking of frames can be performed on non-IP traffic. And then the layer 2 also marking of the frames is the only QoS option available for switches that are not IP aware. While the layer 3 marking will carry the QoS information end-to-end. The marking layer 2. 802.1q is the IEEE standard that supports VLAN tagging at layer 2 on Ethernet networks. The 802.1q implemented two fields are added to the Ethernet frame. Okay. So the 802.1q standard also includes the QoS prioritization scheme known as IEEE 802.1p. That is the standard uses of the first 3 bits in the tag control information or TCI field, known as the priority field or PRI. This is a 3-bit field and it identifies the class of service or COS markings. Marking the layer 3. The IPv4 and IPv6 specify an 8-bit field in their packet headers to mark packets as shown in the figure 9.11. So, in the left. So, both IPv4 and IPv6 support 8-bit field for marking. The type of service or TOS field for IPv4 and the traffic class field for IPv6. These fields are used to carry the packets marking as assigned by the QoS classification tools. The field is then referred to by receiving devices to forward the packets based on the appropriate assigned QoS policy. The 64 DSCP values are organized into 3 categories. The best effort, the expedite forwarding or EF, and the assured forwarding or AF. For the best effort, this is the default for all IP packets. The DSCP value is 0. And then for the expedite forwarding, the RFC3246 define EF as the DSCP decimal value 46 or binary 101110. The first 3 bits or 101 map directly to the layer 2 of COS or cost of service value 5 used for voice traffic. At layer 3, Cisco recommends that EF only can be used to mark the packets. Okay. Assured forwarding or AF RFC25597 defines AF to use the 5 most significant DSCP bits to indicate queue and drop preferences as shown in figure 9.13 in the left side. And then the 3 most significant bits are used in the designate class. The class 4 is the best queue and the class 1 is the worst queue. The 4th and the 5th most significant bits are used to designate the drop preference. The 6th most significant bit is set to 0. Trust boundaries. Trust boundaries or traffic should be classified and marked as close to its source as technically and administratively feasible. Trusted endpoints have the capabilities and intelligence to mark applications traffic to the approximate layer of 2 cost and layer 3 DSCP values. Secure endpoints can have traffic marks at the layer 2 switch. Traffic can also be marked as layer 3 switch or routers. Remarking traffic is typically necessary. For example, remarking cost of service values to IP precedent in DSCP values. The congestion avoidance. The congestion management includes queuing and scheduling methods where excess traffic is buffered or queued and sometimes dropped, while it waits to be sent on an egress interface. Congestion avoidance tools are simpler. They monitor network traffic loads in an effort to anticipate avoid the congestion at common network and intra-network bottlenecks before congestion becomes a problem. These tools can monitor the average depth of the queue. Some congestion avoidance techniques provide preferential treatment for which packets will get dropped. Shaping and policing. Traffic shaping and policing are two mechanisms provided by Cisco iOS QoS software to prevent congestion. For the traffic shaping retains excess packets in a queue and then schedules the excess for later transmission over increments of time. The result of traffic shaping is smooth packet output rate. Okay. For the traffic shaping, it implies the existence of queue and sufficient memory to buffer delay packets, while policing does not. While in policing, it is commonly implemented by service providers to enforce the Contracted Customer Information Rate or CIR. And this is the end of the